Okay, so last time we ended with the definition of terminal singularities. So let me recall that. So we'll say that Y has terminal singularities. If, well, one KY is Q Cartier, and for any resolution, F from X to Y, then we have that KX is Q linearly equivalent to KY plus sum of AI EI, where this sum runs over all exceptionals. And the AI are strictly bigger than 0. Okay, so that was our definition. That was the last thing we ended with, is definition of terminal. And then there was a question of why is this independent of the resolution, and I tried to kind of briefly say that in words, but I missed an important point, which was the next example that we didn't get to, which is that smooth varieties have terminal singularities. So example, which of course you'd hope this is true because smooth varieties have no singularities, but it's not completely obvious from the definition. So if I is smooth, then it has terminal singularities. Let me close these pings because I forgot to do that at the beginning. Okay. And so given this example, which I'll leave as an exercise, then we can argue that having terminal singularities is independent of a resolution, because if we have two resolutions, say x and x prime, well, they're both smooth, and then we can dominate them by a third resolution. And now the discrepancies for x double prime over x and for x double prime over x prime are both strictly positive because x and x prime are smooth. Sorry, I forgot to give the word. So these AIs, which are denoted sometimes A of AI comma X, are called the discrepancies. We'll define a more general notion in a second, but I forgot to write it down here. That's pretty important. Okay, so yeah, so because X and X prime have terminal singularities, since they're actually smooth, then the discrepancies of divisors on X double prime are strictly positive. And now if we have any divisor on X prime that we don't see on X, then we have to see it on X double prime because of this common resolution. And so it'll also have a strictly positive discrepancy because it's lying over something smooth. So essentially things can only get bigger once you've already resolved. So lower bounds are okay. And this also leads to kind of a more general notion. So we can talk about these discrepancies, these AIs. They don't really depend on the resolution. So here I should have written Y. They they really just depend on the divisor as some abstract thing lying over y, and the way we can talk about that is in terms of valuations. So let me just give some essentially just language. So if we look at the function field of our y, then any divisor e that sits inside of some resolution x to y, or any birational map really, this gives us a valuation, a discrete valuation on the function field of x, but that's the same as the function field of y because it's birational. That just measures the order of vanishing of a function along this e. And essentially, by definition, these discrepancies, these AIs, are computed with respect to this order of vanishing because you're measuring the difference of the valuation for kx versus f upper star ky. And so these v's determine the a's. But if we had some other x prime, just some other birational map to y that's isomorphic to x over the generic point of e, so let's say this G is whatever birational map between x and x prime. If G is an isomorphism over the generic point of E, then the valuations are the same because the order of vanishing only depends on the generic point. So that implies that the discrepancies are the same. And that's why kind of in the notation, we just write down a divisor and y, and we don't actually write down the specific resolution that this divisor comes from because it actually doesn't matter. And so kind of the terminology is that E is a divisor lying over y, where we don't actually write down the specific x that it lives on. It's just E is some divisor that lives on some x, which is birational to y, and we take all our divisors up to the equivalence relation, where if we have some E prime on another x prime, where x prime and x are isomorphic over the generic point of the divisors, then we consider them the same divisor lying over y. But which is to say that they're the same valuation. So E is a divisor lying over y, and we consider them up to equivalence coming from inducing the same valuation. And here, I guess maybe I should have written it down. What is this valuation? It's the order of vanishing of a function along E. Okay, so in that sense, these formulas we should really think of as, or we can think of these AIs as depending only on these valuations, but not any valuation. There are specific valuations that come from divisors, and these are called algebraic valuations. And that's another reason why we never actually write down the resolution in the definition of these AIs. We always write it as A of EI, comma Y. Okay, any questions about the definition, the terminology, or the independence? Okay, and there's one more piece of notation that I forgot to define here. So if we have this divisor lying over y, then we'll define the center on x of E as the closure of the image of E inside of X. And so again, here, this is going to be independent of the actual X we chose our divisor living on because we're taking the closure. So it just depends on the generic point of E. And so any two X and X prime that contain the same divisor, that contain the generic point of the same divisor will have the same center. So this is some other invariant. So essentially there's two invariants of divisors lying over Y. There's the discrepancy and then there's the center. We also have a lemma that's analogous to the one from canonical singularities, which is another way to see that it's independent of the choice of resolution, which is that Y has terminal singularities if and only if there exists some resolution f from x to y such that f lower star ox of mky minus e is isomorphic to mkx minus e is isomorphic to oi of mky, where mky is Cartier. And E is the sum of the EI is what's called the reduced exceptional divisor, so we don't take any multiplicities. So this was analogous to the original definition we gave for canonical singularities that we then transformed into a numerical definition. And the difference here is that we have this extra space to subtract off a copy of E. So what this is saying in words is that up to taking this multiple to make K Cartier, it's saying that n forms on Y pull back to become forms on X which vanish along E. So they extend, up to taking this multiple to make it Cartier, they extend, but they're actually zero along E. While in our definition of canonical was saying that forms on Y pull back and extend to holomorphic forms on any resolution. They're regular. Here it's saying that not only are they regular for terminal singularities, but actually they vanish along the exceptional divisor. That's what twisting down by this E is saying. And the proof, it's essentially exactly the same as before. Just notice that when we write down our equality, it becomes after we multiply by m, it becomes mkx is equal to f upper star ky plus, there's an m there, f upper star mky plus sum of mai ei, where the mai are strictly greater than 0. That was our definition of terminal. But now the point is that when we have this m in here, they're actually integers. So the mai are actually greater than or equal to 1. And so we can rearrange this to write down mkx minus e is equal to f upper star mky plus sum mai minus 1. Because remember, this e was this reduced exceptional where the coefficients were 1. And so mai minus 1 is now greater than or equal to 0. So this term is effective. for terminal ones. And so just like the argument before, when we push forward, the effective thing doesn't contribute to the sections. And so we get that the sections of mkx minus e are the same as the sections of the push forward of f upper star mky, and then reverse the argument to go the other way. So the key point is, in this terminal case, we have this extra that once we clear denominators, we have to be at least 1, and so we have this extra room to subtract by e and still be effective. But then beyond that, it's exactly the same argument. So maybe the summary or upshot of all of this is that now we found a class of singularities where smooth is a subset of terminal, is a subset of canonical, and we saw that if we start with something smooth and apply a divisorial extremal contraction, we end up with something that's at worst terminal. And if we start with something smooth and take its log canonical model, its canonical model, if it exists, then we end up with something with canonical singularities. And so these are some natural classes. The other thing that we've observed is that these are determined by these discrepancies, these numbers that tell you how the canonical changes. And we saw that as the discrepancies get bigger, the singularities get better. Because in the canonical case, the discrepancies can be as small as 0. In the terminal case, they can be strictly bigger than 0, and the singularities get better. And in the smooth case, we'll see in a little bit, then the smooth case, they're actually 1. And so you're getting even better. Okay. Let me give some examples. So the first important example, which explains kind of after the fact why one of the reasons why surfaces are such a simpler setting for the minimum model program is that terminal surfaces are smooth. And this we essentially already saw this because we already saw in our case in our minimum model program for surfaces that every time we applied an extremal contraction, we were blowing down a -1 curve or mapping to something lower dimensional. And when we blow down a -1 curve, we ended up with a smooth surface by Castelnuovo's theorem. So this kind of explains why it had to be that simple. So to prove this, so remember, let's say f from x to y is some resolution. So let's not assume that y is smooth, but y is terminal and two-dimensional. And let's say that the exceptional is this union of EIs. Then we know that the intersection matrix EI, EJ is negative definite by Hodge index. And so, okay, well, let's write down our formula. We want to write down Kx is equivalent to some expression of the form f upper star ky plus the sum of ai ei. And by our assumption, we know that these ai are strictly bigger than 0. So now there's like a linear algebra lemma, which I won't prove, but basically says that that this negative definite assumption implies that this sum of ai ei, or maybe, sorry, I should write it this way, implies that there exists a specific exceptional curve EJ maybe, such that this sum of ai ei times EJ is actually negative. So here we're using negative definite, and we're using this assumption that this is a strictly positive linear combination. Okay, so that's some linear algebra. So now we look at that EJ, and let's see what a junction tells us about that. So we know that kx dot EJ is equal to f upper star ky plus some aiei times EJ, which this f upper star ky times EJ is 0. This is 0, and this, by our linear algebra observation, is negative. So this whole thing is less than 0. So kx thought this particular EJ is less than 0. But on the other hand, we also know that EJ squared is less than 0 because it's exceptional on a surface. And then this implies, this is like a lemma on like the second day of class, that EJ is isomorphic to P1, is a -1 curve. And so we can blow down this EJ and factor our resolution through another smooth surface that we get when we blow down EJ. Like Casanova. But now we're in the same situation with f prime. So now f prime must or x prime must also have a -1 curve in its exceptional locus. So then we keep going, and eventually we find that because the Picard rank gets smaller every time, that actually y itself has to be smooth because we just keep blowing down. Okay, so that gives us our terminal surfaces. They're just the smooth ones. So here's an example of canonical singularities, which we did kind of see, or maybe more generally, let's say we have C in P2 is a degree n curve. And let's take X to be the cone over the C, lying inside of A3. And if you want, you can compactify it, but we're just asking about the singularity near the cone. So our picture, we have our C, and then here's our X. And now we have a kind of canonical resolution of a cone. I'll call it X tilde, but it's really the total space of the line bundle O minus 1 for a C inside of this particular embedding. The cone is the space of lines lying over C, and O minus 1 is the line bundle of lines that P2 parametrizes. So that looks like, well, we introduce C itself as an exceptional divisor, and then we just have these line bundle directions like this. And so there's just one exceptional divisor, which is just the 0 section, and to get the cone, we're contracting it. So now we can compute. So E squared is the degree of the normal bundle of E inside of this X tilde, but this X tilde is the total space of this O minus 1. So the normal bundle is just O minus 1. which is minus n because we have a degree n curve. And so that gives us e squared. And now we also know that k x tilde plus e restricted to e is ke, which has degree 2g minus 2, and you can compute the degree, the genus of a degree n curve, and this is n times n minus 3 by using adjunction on P2. And so now let's write down kx tilde equals equals f upper star kx plus, there's only one exceptional, so we just have one number ae. Then kx tilde dot e is n minus 3 minus e squared, which is minus n, so it's plus n, which is n times n minus 2. On the other hand, on the other side, we get f upper star kx plus ae dot e is equal to, well, f upper star kx dot e is 0, e squared is minus n. Sorry, so then this is minus an. These two things are equal, so a is 2 minus n. So that's the discrepancy for this cone over a degree n curve. And now we can see if n is 2, well, if n is 1, then the discrepancy is 1. And then what's the cone? Well, the cone is just P2 or A2. If n is 2, so if n is 1, then we get a smooth cone and a equals 1. If n equals 2, then we get the usual cone, like the quadric cone, say like y squared minus xz, which is singular, but a is 0, so this is a canonical singularity. And if n is greater than or equal to 2, and greater than or equal to 3, then it's worse, it's not canonical. But actually, when n equals 3, this a is minus 1, and this will also come up later. These are called log canonical singularities, which will come up at the end of class today. And then for n greater than or equal to 4, the singularities are just bad. And we'll see later in class why you basically just can't say anything about the discrepancies of the singularities when n is greater than or equal to 4. Okay, so that was one example. We can also do the same thing in higher dimensions. So let's say we take a surface in P3 of degree n, and again let x be the cone. With the same resolution, with exceptional divisor isomorphic to S itself. And now what's E squared? Well, I won't say what E squared is, but we can run the same type of argument. Let me just summarize it. So kx tilde is f upper star x plus ae, but for these kind of adjunction arguments, that's what we're going to use to compute anything, we really want to add e to both sides because we want to restrict kx tilde plus e to e. So we already saw that up here, that the computation was really about kx tilde plus e. And so if we add e on both sides, we get a kind of modified form where the coefficient is now 1 plus a. And this you can call the log discrepancy, and we'll see why a little later in class when you add one. So now we want to compute with this equation. So kx tilde plus e restricted to e by adjunction. This is the canonical of S, which by adjunction on projective space is the restriction of n minus 4. Because S is a degree n hypersurface, and kp3 is minus 4. So that's OS of n minus 4 for this particular projective embedding. On the other hand, again, f upper star kx is 0 on S, and this 1 plus AE restricted to S will be the line bundle corresponding to the divisor 1 plus A E restricted to E. And sorry, I'm like going back and forth between line bundle notation and divisor notation. But so this will be 1 plus A times the normal bundle, and the normal bundle is O minus 1. So this is OS of minus 1 minus A. And so now we have this numerical equivalence between n minus 4 and minus 1 minus A times the hyperplane. And so we get that 1 plus A is equal to 4 minus n, and so A is equal to 3 minus n. So very similar to the above computation, but now we have a 3 instead of a 2 because we're on a 3-dimensional cone rather than a 2-dimensional cone. And so now we'll see our first example of something that has terminal singularities but isn't smooth. So, well, when n equals 2, this is the cone over a quadric surface. We can write down explicit equations that say xy minus zw equals 0 inside of A4, for example. That's one particular cone. So xy minus cw, the projective variety is smooth, but the cone actually has a singularity at 0. So you can just check that xy minus cw is actually singular at the origin, but A is 1. So this is a terminal singularity that's not smooth. So this is singular, but terminal. So we see that in threefolds, we really do have to work with singularities after extremal contractions. And you can check if you take the resolution in this case, then this cone is really the image of some divisorial extremal contraction on the resolution. And then for n equals 3, then we have A equals 0. And then this is the cone over a over a cubic surface. And this is has canonical singularities. For n equals 4, we have, again, these log canonical singularities that I haven't defined yet, but you can maybe guess what they are. Essentially, A is at least minus 1. And then for n greater than or equal to 5, it's bad. Okay. So we're basically going to generalize everything we've been talking about to pairs x comma d, where x is, as before, some normal irreducible quasi-projective variety. D is some Weil divisor, some Q Weil divisor of the form AI di, where these are prime and the AI are rational numbers. So this is some Q of A divisor. We'll call it a log pair. We'll say that x comma d is a log pair if kx plus d is Q Cartier. So note, in this definition, neither kx nor d themselves have to be Q Cartier, only the sum. And then we'll call it d a boundary if these coefficients are actually between 0 and 1. So in a lot of sources, what you'll see is just the definition of a log pair as just a pair x comma d, where d is a Q of A divisor, and then you'll see the Q Cartier assumption and some bound on the coefficients being between 0 and 1 in the assumptions of theorems and propositions, but you almost always need to assume at least Q Cartier, and oftentimes the coefficients being between 0 and 1 for basically any of the results. So I'd rather just build these things into the definition. So for one, you need kx plus d to be Q Cartier because, well, what we want to do is generalize everything we've talked about to the setting where kx plus d replaces kx. And so we need to be able to intersect kx plus d with curves. We need to be able to pull it back and talk about discrepancies. So for that, for any of these things to make sense, we need Q Cartier. Two, needing d to be a boundary is a little more subtle, and it's related to the various vanishing theorems that we'll prove for pairs that really require the divisor to at least be effective, and oftentimes to even have coefficients strictly smaller than 1, let alone just 1. So a lot of the definitions only require kx plus d to be Q Cartier, but then because of these vanishing theorems, the results often require this extra condition of the coefficients being in this range. Okay. So let me give some more notation. We'll call the roundup of the divisor with this notation to be the divisor you get when you take these AIs, which are rational numbers, and just round them up. So now this is some z divisor. And similarly, the round down where you round down these rational numbers. So these are both just regular Bay divisors. And then we'll say that d is reduced if d is equal to its round down. Well, let me add this. D is reduced if d is equal to its round down and d is a boundary. But another way of saying that is just that all the coefficients are just 1. So this is matching with the notion of taking the reduced exceptional divisor, where we just take each divisor with coefficient 1. So a reduced divisor in this field means a divisor where all the coefficients are exactly 1. Okay, so I guess I'll write kind of the motivation more formally. So now in everything that we will do, kx plus d will be the main player, or the main focus, generalizing kx in the case that d is empty. So this will include everything that we've already talked about, but will be a more general and more flexible theory. So this is this log canonical divisor. Essentially because this terminology comes from the fact that if x is smooth and so is d, so both are smooth, then OX of kx plus d is exactly the sheaf of top forms with logarithmic poles or simple poles along D. And it's also the wedge of this sheaf that's called omega 1 log D, which is the sheaf of one forms with log poles along D. So kind of in local coordinates, this omega 1 log D is generated by like dx1 over x1 wedge up to dxn, where D is the vanishing of x1. So it has this dx1 over x1, which is this logarithmic differential as one of the generators. So that's where all the terminology, that's why people throw in log everywhere whenever we have these pairs. That's why we call them log pairs. This is also one of the motivations for studying log pairs because, and it won't really come up in this class, but here's maybe the philosophy. If U is some smooth but not projective or not proper variety, then you can construct invariants of U by taking a compactification that's smooth and with the boundary, and that's also where the name boundary comes from, being a simple normal crossings divisor. Then any invariants that you build out of this sheaf of log differentials on X, these are invariants of the original U. So by that I mean if you take sections of various wedge powers of this thing, global sections. So that's some other philosophy that if you want to study non-proper varieties, you compactify them, add in this divisor D in your boundary, and then log differentials and geometry of your compactification with respect to this boundary encodes the geometry of this non-proper U. But that's not really what we'll be doing. But that's one motivation. Maybe for us, more important motivation comes from just the proofs of things like the cone and contraction theorem. One, using these log pairs gives us some flexibility. So by that I mean, let's say we want to study some variety where kx is not Q Cartier. Then we can't do anything with the previous program. But if we generalize to this log pair, we can find some divisor where kx plus d is Q Cartier, even though kx is not. And then we can still use the tools of the minimal model program to study x with this boundary divisor d. But another reason, so still under this flexibility, is that we can also, maybe we want to study k-trivial varieties, and then the canonical, like let's say we know we have a variety that's k-trivial. Then we have no more information. The minimal model program doesn't tell us anything else about x because k is already trivial, so we can't understand any of the geometry, but we can add some divisor, some boundary d, and now the log minimal model program for this kx plus d will contain information about the birational geometry of x, even though if we just do the usual minimal model program, like we're done. There's nothing left to do. And then another reason is adjunction, which for our Cartier divisors told us that kx plus d restricted to d was kd, lets us relate log MMP of pairs x comma d in dimension n plus 1 to usual MMP, or we'll see a more general version where you actually have log MMP in both versions, but here where we just have this kind of classical adjunction statement to just usual MMP in dimension d. So this gives you the flexibility of inductive arguments. And then D, the canonical bundle formula that we saw for K-trivial fibrations. Where we saw there the base of an elliptic fibration was really one of these log pairs where it was equipped with a divisor. So that's another way. So these last two steps give us tools to use induction on dimension to prove statements. We actually saw a fifth place already, but I didn't write down the proof to save time, and we'll see it in general. But even in surfaces, we saw in the proof of abundance for surfaces, where in the general type case, where we said if you have a general type minimal model, then Kx is actually semi-ample. There, I just said that the proof relies on a more general form of the base point free theorem that we're gonna prove, and the more general form of the base point free theorem that we needed there was in this log setting, where you have this pair. Even though we were applying it to the case where we just had a variety without a divisor, even there, to prove abundance in this general type case, you actually will see that we actually need the base point free theorem in this log setting, and we need to use Kx to pick an appropriate D to prove the theorem. I think I skipped this argument at the time. I don't really remember though. Okay, any questions about the definition of pairs, motivation, etc.? Okay. So now we want to talk about singularities of pairs. So we need to define log discrepancies, or discrepancies in the log case. Those are two different things. Okay, so let's say that x comma d is a log pair, where again, for me, log pair will always mean that kx plus d is Q Cartier, and maybe just regular pair will mean possibly more generally where it's not Q Cartier. But that's not, some sources don't include that in the definition and just add Q Cartier to the assumption of every theorem. And now let's say f from y to x. Now I switched my notation from last time, from the previous part, but okay. So let's say f from y to x is a log resolution. So recall that meant that the strict transform of D union the exceptional with simple normal crossings. So smooth components that intersect transversely like hyperplanes in affine space, like coordinate hyperplanes. Then, so we know that if E is this reduced exceptional, we know that on Y minus E, these are isomorphic. And so we know that the sheaves F upper star OX M KX plus D, a line bundle, so let's pick an M. That makes this a line bundle. So this pullback restricted to Y minus E is the same as this restricted to Y minus E. And so there have to exist unique numbers A of EI, X comma D, rational numbers, such that M KX plus D is linearly equivalent to F upper star M KY plus D, so plus strict transform. I keep confusing my notation from flipping everything around. So this should be strict transform. Sorry about that. Of D on KY, and this should be KX and just D. Plus sum of these rational numbers, A EI X D EI. And this is an actual linear equivalence because I have these M's everywhere, and here I should put an M as well, MAI. And so this gives us a linear equivalence, Q linear equivalence. Of this form. Okay, and so we can define these numbers to be the discrepancies. So this A of the exceptional EI. Okay, but we also have this F lower star inverse D here, the strict transform. So it's sometimes useful to have uniform language for discrepancies of divisors that aren't exceptional. And they're essentially going to be these coefficients, but they're going to be negative because we're going to subtract them over. So let's also define the discrepancy of any divisor on X, so where P actually lives on X. So we can think of it as a divisor over X, so any divisor on a resolution that still maps to a divisor to X, so P is some prime. Then we can define the discrepancy to be minus AI if P is one of the divisors appearing in our boundary, or 0 otherwise. And now we have this notion of discrepancy for any divisor, not just the exceptionals. And then with this more general notion of discrepancy, we can write KY is linearly equivalent to F upper star KX plus D plus the sum over all prime divisors of the discrepancy of that divisor times that divisor. So that's why we have a minus AI, because we subtracted it over. And this whole thing will sometimes be denoted AY of X comma D as the discrepancy divisor. Yeah, so this thing's sometimes called the discrepancy divisor. It gives you the difference between the canonical upstairs and the log canonical downstairs. And you can also talk about the log discrepancy. B of an exceptional is just 1 plus A. It's the log discrepancy, and that's the thing that appears if you rearrange this formula and write it as ky plus strict transform of D plus reduced exceptional E is equal to F upper star kx plus D plus sum of now the log discrepancies of exceptionals EI. And so this is useful as we saw in these computations where it was easier to compute with the divisor where you add the reduced exceptional than it was to compute without the reduced exceptional there. So it just depends on the proofs that you're working with, whether you want to work with the log discrepancy or the discrepancy, but it's the same. And so I want to make one more remark where here we're using these linear equivalences, but oftentimes you'll see discrepancies defined and talked about just in terms of numerical equivalence because that's how we're going to compute anything. And so the issue is if you put numerical equivalence everywhere, then these formulas don't uniquely determine this discrepancy divisor. Because now if you allow up to numerical equivalence, then maybe your divisor in AY is numerically equivalent to some other divisor that's just not this particular one. So let me write down the fix for that. So if you write down, say ky is numerically equivalent to f upper star kx plus d plus some a, which is usually what people do in proofs, then this a, or this discrepancy ay x comma d is uniquely determined by being the unique a that you can put in this numerical equality such that the push forward of a is minus d. And this is by a negativity lemma that we secretly already used, but we'll prove formally a little later because for now it's good enough to just work with rational equivalence. Somehow it's better to work with rational equivalence, but it's easier to work with numerical equivalence. But this negativity lemma that essentially says that the exceptional divisors are just uniquely, and their discrepancies are just uniquely determined because they're exceptional, so they don't move. And so to pick out this A, all you have to do is stop the D from moving. And so you do that by just declaring that A is the divisor where the push forward is actually your original D as a divisor, not just as a class. So that's essentially this negativity lemma is the thing that tells you that kind of the exceptionals are negative, so they can't really move around and they're uniquely determined already. Okay, but yeah, we'll see that a little later in the class, the actual negativity lemma. Okay, and this log discrepancy thing, just kind of philosophically, what's happening here is that in certain results and certain arguments, it makes sense to think of the pair y with boundary f lower star inverse d plus e as like the fundamental thing, while in other arguments, maybe it makes sense to just think about the pair y comma f lower star inverse of d, and that's kind of the philosophical difference between working with the log discrepancy and the discrepancy. Whether this is kind of the fundamental pair structure that you want or not. So this is really the flexibility that we get from pairs. We get to pick which divisor we we use as our boundary, depending on what's better suited for the particular thing we want to prove. Okay, so I'm gonna, in the next 5 minutes, I just want to write down a few exercises that I'll leave as exercises that are just useful for computing and working with discrepancies. And speaking of exercises, if there's anybody who needs who's enrolled in the class and needs an actual grade, I am planning on writing up these exercises into an actual problem set very soon. Okay, so first one, let's say D prime is some effective Q-Cartier divisor. Then we can ask about what happens to the discrepancies when we add this D prime. And the statement is that for any prime P lying over X, the discrepancy of P is greater than, with respect to the boundary, some boundary D, is greater than or equal to the discrepancy with respect to this D plus D prime. So if we add a divisor, if we add something effective, then we're making the discrepancy smaller. So it's like a monotonicity, but it's like a reverse monotonicity. Or another way to think of this is saying that if you add a divisor, you make the singularities possibly worse. Maybe they're the same because it could be inequality, but they could possibly get worse because we already saw for canonical and terminal singularities, bigger discrepancies are nicer singularities. They're closer to smooth. And then this is in strict inequality. If and only if the center of this P is contained inside of this D prime. So of course, if we have some divisor that's just away from the D prime, then this is saying it's not going to change the discrepancy at all because the D prime isn't affecting the log canonical divisor in a neighborhood of P. And so we only get something strictly bigger if our P is actually mapping into this D prime that we've added. Okay, so that's exercise 1. 2, I guess I need a definition before 2. So I actually don't need a definition. Let me write down the exercises, then I'll give the definition probably next time. So 2 tells you how discrepancies behave for smooth blowups. So let's say X is smooth and Z is some irreducible subvariety. And then we can look at the blowup on Z. This has some exceptional divisor E that maps to Z. If Z is smooth, then the exceptional locus is actually just a divisor. So then E is the full exceptional locus. But more generally, we can consider cases where Z is not smooth, and then the exceptional locus might have some other parts in it, but it always has a unique divisorial part, and we'll just call that E. Then, and let's say that D is sum of AI DI as before. Then the discrepancy of this E has a very explicit formula. It's K minus 1 minus the sum of AI multiplicity along Z of DI, where this K is the codimension. Okay, so that's another exercise that's useful for some computations. And then the third one essentially says that the discrepancies don't change if you have a birational map that itself has no discrepancies. So if f from y to x is proper birational, and these are equipped with divisors dy and dx, such that, well, the divisors are related by push forward, and ky plus dy is just equal to f upper star kx plus dx. So there's no discrepancies for this map F. Then for any prime divisor lying over both of these, but we can just say lying over x, the discrepancy of P for the pair y comma dy is the same as the discrepancy for P for the pair x comma dx.